This is a Triple J podcast.
Hello, welcome back to another week of answering your science questions. Dr. Carl is on sabbatical, so Bianca Nogrady is stepping in. And this week we had questions about the brain, about the heart, and with that, actually, time of death. We'll get into a bigger conversation about that later on. We also chatted rising sea levels and whether our bodies would adapt to work with that. Basically, would we become fish people? I'm Lucy Smith. Let's get into it. Bianca, how you doing this week?
Oh, I'm doing pretty good, wrestling with a little bit of a, throaty coughy thing, but not the spiky cough.
It's about that time, right? Where we are kind of getting these little moments. I've been going through a bit of a hay fever moment as well. Is there anything you can tell us, actually? I'm putting you on the spot here as we kind of get into cold and flu season. Is there anything scientific or interesting you can tell us about colds or flus or viral things?
Sure. So one of the interesting things with COVID was initially we were looking at what we thought was a seasonal pattern. So, for example, flu tends to have a seasonal pattern. So you'll see, like in different countries, you'll see it kind of peak at certain times of year and then it'll decline. And that pattern is fairly predictable. There is a seasonal element to it, as in it's associated with, for example, winter. And the reason why we do get a higher frequency of flu and colds and things in winter is literally just because we're all indoors. We spend more time indoors, packed together. The air is damper. We're closer in. And because it's cold, maybe our immune systems aren't really kind of quite up to scratch. So that does make us more vulnerable to infection. But what was interesting with COVID was that it started out being seasonal, but then it completely changed. Yeah. And as it became more and more infectious, that sort of idea that it was going to be dictated by our proximity to each other kind of went out the window because it was just spreading so easily. And measles is another one like that, where it's so contagious that it doesn't really matter what season it is, because outdoors, indoors, whatever the setting, the risk is still so high that it kind of smooths out all of those issues. But something like hay fever, obviously definitely a seasonal element because that's going to associate with pollen, so you're going to see more of it in spring and summer. But colds and flu are a kind of seasonal, but mainly because of that kind of proximity and weather.
Okay, so do you think you can avoid a cold by dressing warm, or do you think it's going to happen regardless?
Well, again, one thing we learned in the COVID pandemic, was that this kind of infection control works. And what was so interesting was when we were all masking, when we were all isolating, when we were told to stay home, when we were sick, that had some really amazing flow-on effects, particularly to more vulnerable groups. So, for example, people who have chronic lung disease, like chronic COPD or chronic obstructive pulmonary disease, they're extremely vulnerable to dying from a simple respiratory infection. That can often precipitate a kind of catastrophic event. And we saw a significant drop in the number of people dying from COPD or dying with COPD because they weren't being exposed to these viruses. So they were, because often it's older people, not always, but often older people. They weren't seeing their kids and grandkids who might have been the ones that would expose them to events. They weren't going out to areas which were packed full of people. And also we were masking, and we know masking works. We know it works. Proper masks work. They reduce the risk of you spreading whatever bacteria you've got viruses you've got to other people. They do lower the risk of you breathing those in. So we did all the right things. It was an amazing experiment to show that we can, in fact, reduce the risk of deaths from these respiratory conditions if everybody actually goes along and does what they're supposed to do. But then, of course, now we're not really doing that anymore, which is a shame.
If you've got any follow-ups or questions off the back of that, 0439 757 555, that is where you can send in your science questions to Bianca Nogrady. We're going to start here with Kevin in Canberra. Dr. Kevin, what's your question?
Hi, so plants have cells and DNA just like animals, right? So my question is, why don't large, long-lived trees and things get cancer like animals do?
That is a great question. And in fact, they do. So cancer occurs, you're right, cancer occurs in animals, which includes us, because it's the result of mutations in our genetic material that ultimately one of those mutations might trigger our cells to kind of divide and grow uncontrollably. And that is what ends up being a tumour, essentially. But our cells are very different to plant cells, but plants do still have that same kind of fundamental process that their cells need to divide, and they need to divide in a healthy way, and they also need to die, because cell death is actually a really important part of health, oddly enough. So what happens in plants is that they can actually get cancers from a bacterial or a viral or a fungal infection, and that can then essentially mess with the plant's genome the same way that, for example, solar radiation messes with our genome, or exposure to cigarette smoke. And they get the same problem. The cells then multiply uncontrollably. You get tumours forming, and you'll actually see these. So the most common one, I guess, a plant tumour is called crown gall. And you've probably seen trees that have like these really, they look like tumours. They look like kind of big outgrowths, not like the kind of smooth, knobbly ones you get where there's been a tree branch that's fallen off. These are real knobbly, crinkly, messy growths around the trunk of a tree. And this is actually called, this is caused by a bacteria called Agrobacterium tumefaciens. And the tumour essentially creates this gall, and it's often around sort of the base of the trunk and sometimes on the roots, because what it's doing is it's essentially inserting its own genetic material into the plant's genome, and then that forces the plant cell to essentially divide uncontrollably. And funnily enough, produce a whole lot of sugary kind of molecules as well, which it then feeds on. So it's kind of, it's providing its own food source, which, to be fair, our tumours do the same thing. They kind of create a lot of blood supply. So tumours have a lot of blood supply in them. Galls are a thing. You probably, if you walk around and look at some trees, you might notice some.
All right, thanks. Do they kill the plant, or does it?
I think it depends. So, for example, I know crown galls or galls tumours essentially are an issue, for example, for wine growers. So grapevine growers. I keep thinking you grow the wine. There's like these plants with whole bottles of wine.
The bottles, yes.
Grape growers, because there are galls that can grow on the roots, and that can actually decrease the productivity of the plant. I would imagine anything that's drawing energy from that the plant would otherwise be putting into its own growth and health. Ultimately, if it gets severe enough, yes, it would kill it. But yeah, I don't know how long that would take.
Thanks, Kevin.
Oh, thank you.
We've got Maddie in Newcastle here. Maddie, what's your question for Bianca?
I was wondering, I have two different coloured eyes, so one's like completely different. So I was wondering, first off, why? Like, only some people have it, and from what I've seen, it's very rare. And then, like, the other thing, I guess, if there's any evolutionary reason, maybe.
Firstly, I can say that is the coolest thing. What the term for your different coloured eyes is heterochromia, which basically chromia, I guess, is colour, and hetero meaning different, or not the same thing. Actually, I have never studied Latin, so I'm possibly getting that wrong, but we had a stab at it anyway. So if you've got two completely different coloured eyes, one, for example, one blue, one brown, then you have complete heterochromia. And so the difference is the colour of your irises. What colour are your irises?
So I've got one that's brown and one that's like a hazily green, I guess. I called Dr. Carl a few years ago around why they change colours and sometimes are more intense than other days. But when I was born, it was blue and brown.
Wow. I just think that's absolutely super cool. So yes, it is very rare. There is another form of heterochromia, which is called partial heterochromia. And that's when you've kind of got an inner ring of your iris that's a slightly different colour to the outer area of the iris. So if you're born with it, it's congenital heterochromia, which sounds scary. It just means that you're born with it, essentially. There's no other consequences. It's not a disease in and of itself in the sort of form that you've got. It can occur as a result of some diseases, and sometimes it can actually result from injury, eye surgery. There are some kind of benign tumours that can actually cause the iris colours to change. But there's actually nothing wrong with it. It's actually in the form that you've got is perfectly healthy. It's just super cool, essentially. And in fact,
so no reason, because obviously I don't have really good eyesight or anything.
Yeah. Not a superpower or anything.
No.
I mean, what would be interesting? I don't know. Do you have kids?
No.
Yeah, I mean, what would be interesting, I don't know if it's genetic. I don't know if there's actually, whether this is something where you're going to be more likely to have kids with heterochromia, or it'd be interesting to kind of maybe look in your family tree and just see if there's anybody else in your family history that, I mean, it's probably hard to go back too far, but whether anybody else has had that. And funnily enough, I think I might have mentioned this last week, I'm not sure, but David Bowie was often thought of as having heterochromia because if you look at photos of him, his eyes look like they've got different colours.
Pupil, but he was in an accident. Believe me, I know. I'm obsessed with Bowie. He was my saviour as a kid, having red hair and two different coloured eyes.
Fantastic.
Kindergarten was not nice.
Yeah, I just looked it up. Anisocoria, where one pupil is permanently dilated, is what Bowie had. But Maddie, maybe the evolutionary benefit, Maddie, is now you've got something that people immediately talk to you about at parties or compliment you on when you're going about your day. So maybe you're just more of a magnetic person.
Well, it's a little bit weird having complete strangers stare into your eyes.
I know.
To see the colour.
Yeah, you don't have the my eyes are up here problem.
Yeah, exactly. Yeah. Thanks, Maddie.
Thanks, guys.
All right, we've got Arabella from Turramurra. Arabella, what's your question?
Hi, so I am wondering, I know when you're in the bath, your fingers get really pruny because it's better to grip onto things. So I'm wondering if the world flooded, would it be possible to turn into fish people, or is that too far for evolution?
Nothing's too far for evolution. It's probably too short for evolution, I think, is the opposite problem. So over evolutionary timescales, I mean, as we have all collectively evolved from creatures that lived in water that then ultimately crawled out onto land and their gills turned into lungs and so here we are, or evolved into lungs so that they could breathe air instead of water. So, I mean, arguably somewhere buried deep in our genetic code are still those potential for those things, those gills to emerge. But for that to happen, you need an evolutionary pressure. So we would, presumably, there would be kind of a very, I mean, we're talking millions, tens, hundreds of millions of years, potentially for that process to happen. But there's no reason that it can't happen. I mean, I guess what's interesting with humans is that because we have technology, if you compare the world that we live in now to even the world that we lived in 100,000 years ago, I mean, it's so profoundly different. Evolution doesn't really operate on such short timescales. Selective pressures do. So, for example, if there was a human who had, by virtue of some weird, wonderful mutation grown gills, then that person would obviously have a very strong selective advantage. But it takes a much longer time frame for that to happen at a population level where all of us have evolved. What's more likely to happen, given humans, we have these big brains and we use technology, is that we're going to technologically evolve to live in that world, whether that be we live on floating islands and we all go, full Kevin Costner Waterworld style. Although incidentally, I think there might be a kid in Waterworld that had gills from memory. Was that part of it was a long time ago since I watched that, but probably not based on science. We're more likely to use technology to adapt in a short term. But in terms of what evolution will do in the long term, who knows? It depends. Maybe by the time that evolution would have done something about it, we would have already left the planet and gone to the stars.
So if we don't use technology, because wouldn't humans then die out before they could evolve to that?
Well, for an event that happens as fast as global sea level rise and flooding, yes. Yeah, I mean, that is a catastrophic event. So, for example, another example of catastrophic, global catastrophic event is the asteroid impact on the Earth that wiped out most of the dinosaurs. I mean, if they had been able to rapidly evolve to be so-called warm-blooded, so that they weren't relying on the heat from the sun, if they, were able to evolve to different diets, then if they were able to do that extremely rapidly, they may have had a chance of survival, but that's not how evolution works. Instead, what happened was that the much, much smaller creatures that were able to forage, that were able to survive on what was left, that were able to survive the colder temperatures, the lack of sunlight, those were the ones who survived and then evolved up into us ultimately, well, chickens, and there was a fair few steps along the way. But it's something as rapid as catastrophic sea level rise, especially given that it's, when it happens, I mean, it is, if on the trajectory we're on, most of the major metropolises around the world will be unlivable. Anything coastal will be unlivable, but there's still going to be a lot of land. So we're more likely to evolve, air quotes, by essentially moving inland and adapting that way, or technologically adapting to live on and in a watery environment rather than physiologically adapting. But no, if we didn't have the technology, then we'd be in deep trouble, as will most species that aren't us.
Yeah, right, okay.
Thanks, Arabella. Nate, what's your question?
Yeah, hey guys. So yeah, since we know already what how we evolved into the humans we are now, is there any hints of what we're going to evolve into, like in regards to like as technology is getting smarter, like are we becoming dumber?
That's actually a really good point.
Short answer, yes.
Short answer, I think we can all say yes, social media has made us dumber. So we have what we were talking about earlier with gills. Like for us to evolve gills, there's a pretty massive physiological reimagining of how our bodies work and how our lungs work and how our blood works. So it's a huge change that would take a long period of time. But on shorter timelines, we have already actually been changing. So in the last, let's say, 100,000 years, we have been getting shorter, which, as a short person, I say yay. We've been getting lighter. Our bones are getting smaller. It's very gradual, but actually, interestingly, has kind of accelerated a little in the last 10,000 years. And we're actually in more recent times, like the last few centuries, average height has started to increase. Now that could be a function of, it's quite likely a function of something like nutrition, that we are actually eating better, we have healthier diets, so we essentially are able to be taller. It could be a function of just literally how we move and how we walk. But there are other evolutionary processes that are going on shorter time frames. So, for example, shorter, like adaptations that happen on really short time frames are if you're living in high altitudes where the oxygen concentration in the air is lower, your body actually adapts. It's not so much evolution, it's more of adaptation, but your body adapts to that by producing more red blood cells so that you actually are able to carry and absorb more oxygen from the environment. But we have also been evolving resistance to certain diseases like malaria. We have also seen, just since, I guess, the emergence of our species, Homo sapiens, we've seen changes in skin colour as well. So, for example, in the Northern Hemisphere, you have got pale skin. Some of that's the influence of Neanderthal genomes, but it's also an adaptation to an environment where it was not an advantage to have melanin in the skin because you were exposed to much less sun. So some of the other kind of things like changing in brain, our brain size is changing. Don't actually know. Well, that's an interesting one because that could also be to do with posture and birth. As much as, big brains don't mean big thinkers. So in terms of where we're going, I mean, you look at how we've changed from how we were, let's say, 20,000 years ago. I mean, we spend a lot of time sitting on our butts. So in terms of how that's changing how our body works and moves, that's a massive change from what we used to do. We get far less physical exercise or physical activity than we would have done even 5,000 years ago. So that is going to be having a significant impact on our physiology. Where it's leading us to is a really interesting question. And I actually don't know how to answer that. I mean, it's kind of crystal ball gazing, but And particularly, things like social media, the fact that we spend so much time literally like 3 feet away from, I'm not even sure how a foot is, but very close to screens. What's that doing to our eyesight? What's that doing to the musculature of our neck because we're holding our heads still in a particular position? What our kind of, great-great-great-great-great-great-great-great-grandchildren are going to look like. They will probably be they'll definitely be slightly different to us, but what that's going to look like at a population level, that's anyone's guess.
That's really interesting because weren't there a lot of old houses which had really short door frames and then we had to make the door frames bigger, but now are we going to go back to shorter door frames potentially?
Well, who knows? I mean, yeah, if we are leading much more sedentary lifestyles, but we're still presuming we still have the same healthy diet. I mean, climate change potentially could actually change that, that it is altering the nutritional content of our plant foods. I mean, we could see us. Yeah, that's actually a really good question. I mean, this sort of you need a physiologist to talk about, anatomist to talk about, well, what impact is sitting all the time having, and does it mean that we will start to get smaller again? I mean, again, short person, yay. But that can have its disadvantages because who's going to reach down things from high shelves for
That's
me?
it. Nate, you've opened up a can of worms. We've got Charlie from Meange in Brisbane. Charlie, you've been asking your friends something. You think you've got a consensus. What's going on?
Yeah, so I always thought it was just me, but I always get really full after I eat. And then when I'm really full, I'm really thirsty. And like I said, I always thought it was just me, but after speaking to my friends, everyone seems to agree. So I just want to know why that is.
Yeah, it's perfectly normal. Essentially what's happened is that you've probably eaten something that might be a little bit salty, especially if you had a big meal, salty, spicy, and so your body is it's got an increase in salt. And to balance that out, it needs to dilute it with water. So it's an instinctive kind of response. And the saltier the food, the more thirsty you're going to get. Sometimes also, and this might just be me, when I've eaten like a big meal but I want to eat more, sometimes I find it's almost like if I just kind of wash it down with water, it feels like it makes more room. That's no scientific basis in that whatsoever. But what's important to note is that excessive thirst, so it can actually be a symptom of disease. So it is actually an early warning sign of type 1 diabetes if you have excessive thirst. But that's something that when you're thirsty all the time and for no good reason. If it's, you're thirsty after a big meal, that's perfectly normal. It's just your body's trying to kind of balance out the fact that you've taken in a whole lot of salt. Even for a normal meal, there's still salt in there and your body needs to dilute it.
That makes sense.
Thanks, Charlie. Jake in Wollongong, what's your question?
Hey guys, hey doctors, how you going?
Good.
Howdy.
Just had a question about cold water therapy. I was just kind of having some appointments through the last year with my doctor, and just keeping an eye on bloods and stuff, especially around the liver. And we noticed that for the 8 months or so, as well as doing the cryotherapy and the cold water therapy, that my liver and my pancreatic enzymes had dropped significantly. And just wondered if there was any, any information available onto how you reckon that could have been working, or...
Yeah, that's a really good question. So cold water therapy, I mean, it is fairly popular. I think it's probably touted by a lot of people that aren't necessarily coming at it from a science perspective, but it does actually, there is evidence that there are certain benefits from it. Whether those would translate to impact on liver function and pancreatic function, I'm not sure, but I will tell you about what we think it can do. So, for example, it's often used by athletes sometimes used by athletes who have a soak in cold water after exercise. There is some studies suggesting that it decreases muscle soreness after they've had a period of exercise. And one of the theories is that when you immerse any part of yourself in cold water, it causes the blood vessels to constrict because your body doesn't want to lose that heat, so it constricts the blood vessels, reduces the blood flow to the area, and so that can actually then reduce swelling and inflammation. So that might be why it helps with muscle soreness after exercise. Obviously, if you're too hot, really great way of cooling down. There's some case studies, so it's just like one person here or there, which can also be anecdotal, suggesting that it has helped people with depression, that it can decrease depressive symptoms. But again, that evidence is a little bit wobbly. It's not necessarily strong evidence. And similarly, there's been studies looking at techniques like cold water immersion, but also meditation and deep breathing, whether those had an impact on the immune system, on boosting the immune system. And again, seem to suggest that there might be some benefits there. But again, our immune system is really sensitive to stress, to psychological stress as well as other stresses. And so one could also argue that maybe this is just actually addressing stress is going to be good for the immune system. So in terms of things like liver and pancreas, I don't know enough to know whether those two things whether related or whether there are other changes that you were making, lifestyle-related changes or other changes that you were making in your life that might have also impacted the health of your liver and your kind of blood levels of things. It's hard to cut. You kind of have to tease those things apart.
Yeah, I think what my GP was kind of getting at too is like my lifestyle, my diet was exactly the same. It has been for the past, 6 years or so. I've got IBS. Yeah. And then so what she found was interesting was, and the way she explained it was when I was getting into the had the cryo chamber or the cold water therapy, the blood was rushing towards things to protect them because it kind of thinks that you're in a bit of trouble. And then when you get out, you're bright red because all the blood comes back to your skin. And she's like, maybe, and that's what I found cool. She's like, she's going to do a bit of research and dive into it because she found it quite interesting that my levels had kind of leveled out for that period of time. So, yeah, lots to kind of work out, I suppose.
Have you continued doing it, Jake?
I stopped for a couple of months and funny enough, ended up with pancreatitis.
Sorry, dude. That's no good.
But we're looking at getting me back into it now because it can get quite expensive if you don't have your own stuff.
Right.
I mean, well, the other thing is cold water immersion. I mean, I don't necessarily know the sort of the finer details of that kind of cryotherapy approach, but it could also be just going for a swim in winter. I know that there are a lot of people that do that on a regular basis. Not my jam personally. I like water to be kind of blood temperature, but that can also be an approach depending on where you live. Is to actually and obviously do it safely, but to do some cold water swimming in winter because I mean even just that's also including physical activity and getting outdoors and all of those things are also just generally good for us. But it's an interesting theory that the GP has about the sort of you kind of causing a big shift in your your blood from your skin moving to your vital organs and then going back out to your skin. I mean, obviously it's in all of those places at the same time. It's not like you shut down. But look, that's one's cool. I guess it's just observing the patterns and seeing what happens.
Yeah. Thank you so much for your time.
Yeah,
Thank
Jake.
you.
Text in maybe when you start up again and see how you're going. We've got Zach in Sydney. Zach, what's your question?
Hi. I have cerebral palsy, and my question is why do brains, like other parts of the body, why do brains not heal like other parts of the body that have trauma? And because I was born 26 weeks early, and I'm just curious, even though I was born that early, why does that kind of thing happen and not heal fully?
Yeah, it's a great question, and it's such an unfortunate thing that nerve cells do not replenish themselves the way that skin cells do. It's it seems to me that it's a bit of a design flaw with our bodies. But yeah, essentially, as you know, if you cut your skin or any kind of abrasion, it heals because your skin makes new skin cells. We have stem cells that are underneath it, constantly replenishing. So we can actually create new cells to replace those ones that have died or been damaged. Unfortunately, that does not happen in our brain and spinal cord, in our central nervous system. So the nerve cells in the brain, which are called neurons, don't actually renew themselves. So what happens is that when brain cells die for whatever reason, whether it's injury or accident or disease or whatever, they're not replaced. Now, the brain has kind of I guess, evolved a way around that. So you probably heard the term neuroplasticity. Essentially what it means is that because we can't replace those dead cells, the brain essentially works around them. And so it will make use of existing pathways to compensate for that change. And this is why, for example, people who are born deaf or have hearing problems when they're born, the earlier a cochlear implant is put in, the better it is, because the longer that they remain without hearing, the brain will actually then kind of rewire in some ways or recircuit. And it makes it in some ways to kind of compensate for the loss of those neural pathways associated with hearing. And so you want to get in before that process happens. But the good thing about neuroplasticity is it's happening throughout our life. I mean, it decreases as we get older, particularly, much older. But particularly when we're younger, our brain is constantly, turbocharging some pathways, other pathways kind of shrink down. We have injury, our brain works around it. So it's really malleable and adaptable, but what it cannot do is replace neurons that are lost, unfortunately.
Right.
So this is particularly important with and why there's such concern around concussion at the moment, because concussion is damage to nerve cells in the brain. Those cells die and it accumulates. And so when you have a concussion and then you have another concussion and another concussion, and what's happening is that there's essentially an accumulation of death, of cell death in the brain, and that can eventually get to the point where it really has an impact on brain function, and that's why we get to the CTE, or chronic traumatic encephalopathy, which is the condition that is associated with repeated concussions, and it obviously is now a major concern in a lot of sporting codes, and this is why.
Thanks, Bianca. Thanks, Zach, for your question.
No problem.
We've got Chloe in Launceston before we get to a break. Chloe, I feel like we had a can of worms opened earlier when we were asked the question if water levels would rise if we would turn into fish people. Chloe in Launceston, what's your question?
Hi. Well, I was just wondering, if the water levels were to rise, would Tassie sink?
Well, it's not so much sink as the water comes up around it. So there have been some efforts to map. Well, there's global efforts to actually map what impact different levels of sea level rise would have around the world. There are, so I'm just actually looking at one for Launceston. Now, Launceston doesn't necessarily seem like a coastal city, but it is exposed because the Tamar is tidal, and so it does actually connect to sea and it connects to sea levels. So, for example, and actually just going back a step, what's interesting to know about sea level rise is that it's not equal around the world. Like it's not like a bathtub where, you put something heavy in the bathtub, like a person, and the level of the water rises equally all around the bathtub. Because our oceans are shifting and moving and they're under the influence of the moon and different landforms, sea level rise is not going to be equally spread around the world. There are some parts of the world that are going to be much, much more exposed and experience much higher levels of sea level rise than others. So in terms of Tasmania, and I'm just trying to picture, I mean, obviously Hobart is going to be in trouble, but it's not like and I've just forgotten the name of the mountain. I'm sorry. This is my bad. The lovely big mountain that you have in Hobart.
Mount Wellington?
I think so.
Yeah, I think so.
I don't know what the indigenous. It has an indigenous name, and that's also skipped my mind. But I mean, obviously, that's not going to disappear. But and I'm trying to think of what else is around the coast. I mean, Tassie's got some quite mountainous areas in the sort of interior. So those, presumably, I mean, I can't imagine that there would be a scenario in which those would completely disappear. I'm trying to think of what the forecasts are for sea level rise around the world. I think for example, the end of this century, I think certainly for Tasmania, the prediction on our current trajectory is about 84 metres of sea level rise, so 84 centimetres by the end of this century. That was forecast from the last IPCC assessment report. So 80, and the other thing to remember is that 80 centimetres doesn't sound like a lot, But then if you've got to imagine adding 80 centimetres onto the top of, like a king tide, or adding 80 centimetres on top of a storm surge. So that's when you start to see the real damage, because that is it's a massive kind of escalation on top of what is the current understanding, what all of our infrastructure has been built to. But you can look up. There are maps that actually, and they're kind of really depressing. Some of them.
I was going to say, I'm like, not great viewing.
Yeah. It's not one to look at when you're feeling a bit delicate. But there are maps that show coastlines around the world and the different predicted levels of sea level rise according to whether or not we actually do manage to stop burning fossil fuels and achieve net zero in a meaningful time frame. It shows what the different levels are that we can expect. But it's not good. I mean, there's a reason why so many major cities around the world are on coastlines. They're fantastic places to build cities. There's access, there's resources, there's everything. And, places like Sydney obviously going to be in trouble.
Chloe.
Oh, I better sharpen up on my swimming skills.
Yeah, absolutely. Evolve some gills.
I know we need to evolve the gills. Chloe, thanks for your question.
No worries. Thank you.
Catherine from Newcastle. Catherine, what's your question?
Hi. I saw on TV last night this amazing scientist has created a mechanical heart, so we don't actually need to have another donation or whatever. But what my question is what happens when our body wants to die, when it's usually the heart that stops beating when we die? What happens to us?
That is such a good question. And look, this is actually, I'd be really interested to know how this will work when people who have this device implanted, because in theory it will continue to circulate blood around the body. I don't know that for sure, but it is electromechanical, so it's not like our heart is obviously biologically driven, and so once we get to the point where either our heart muscle simply can't send those electrical impulses and stops beating, then we die, or we've lost too much blood or whatever it is. In the case of this, so what's firstly interesting about this is that it's not a rhythmic beat. So this heart does not beat. It's actually it's a pump. It's a continuous pump, which is extraordinary. So somebody with this will not actually have a heartbeat. It's kind of like a pool pump. It's just going to kind of keep going. But it's interesting, what you've brought up is actually a really important discussion that's going on. Well, it's been going on for a long time about when are we dead? Because you said when your heart stops beating that you're dead, but we can restart hearts. We can even replace them. We can actually have an external process, so cardiac bypass, where a machine can circulate your blood for you. So then if your heart keeps going, when are you dead? And this is where you get to the discussion about the difference between brain death and cardiac death, and which of those is relevant. And I say this because I wrote a book about this, so this is why I'm. It sounds weird to say this, but a big death nerd. But something like this, where you have an artificial heart that in theory can keep going even when the person whose heart it is, when their brain has ceased to function, that will be an interesting decision then about whether, we can't restart a brain. That's what we do know. We cannot restart a brain. We cannot replace a brain. So I guess in this case, this individual, the idea that they might die from heart disease has or that they'd be pronounced dead because their heart has stopped beating, is actually off the table. So it's a really, really good question, and it's a fantastic invention because, currently the best technology we have to replace hearts, or to at least to fix hearts that are damaged, is either a complete transplant, which is a huge operation and obviously very, very lots of potential things that can go wrong, or you can have an external device. But as soon as you have something that goes from outside the body through the skin, through your barrier to inside the body, there's a risk of infection. So, to be able to completely replace a heart with a device like this, a machine, is an extraordinary development. But yes, it will prompt some policies, some questions, and I guess some frameworks around how do we know when this individual has died.
Wow, thank you.
So interesting. Catherine, thanks so much for your question. What was your book called about death?
Oh, it's just called The End.
Wow. The End by Bianca Nogrady. You can go and check it out. Bianca, you are joining us for the Science Hour for the next few weeks. This full episode you can check out via the Science with Dr. Carl podcast, wherever you get your pods, and via Triple J's YouTube channel. Bianca, we'll do this again next week.
Absolutely. Look forward to it.
And that's it. Bianca Nogrady will be back with us next week, covering for Dr. Carl while he's on sabbatical. And you can continue the conversation in the YouTube comments on Triple J. We are uploading these episodes. Maybe you've got a follow-up question. Feel free to add it there. Or you can listen anytime, wherever you get your podcasts or the Triple J app. My name's Lucy Smith. This episode was produced by Josh Brennan. And we'll catch you next week. Bye.
Dave Marchese here from the Triple J Hack team. Hey, if you love Dr. Carl's podcast like I do, you might enjoy the Hack podcast as well. Each day we bring you the news that matters to you, from the latest science on climate change to what's happening in politics and news around the world. The Hack podcast. It's your daily fix of the news you need to know. Get it wherever you're listening now.